folks, today we're going to talk about the t-test. The t-test is used for means. We just finished some work on proportions and we use the one proportion z-test for proportions. For means, we're always going to use the t-test. Just like when we did confidence intervals, we used the t-star for means because the standard deviation of the population is not known. So a t-test is used to see if a sample provides an X bar that is very unlikely given the assumption about the mu, the mean for the population. And so you're hoping to find an X bar really far away. I'd like to just walk you through an example of a t-test, the battery problem, which is located in the 9-3 notes that are on the Schoology post for this week. So let's say a company is hoping to improve the length of time that a battery holds charge for AAA batteries. And in the past, they've had a mean of 30 hours, but now they're new and improved, and they're trying to, advertise that their batteries actually last longer than 30. So they're hoping to find a sample that has an X bar really far away from the 30 so that they can say that it's unlikely. Okay, so if I wanted to do a test here, a formal test, I would state my null and alternative, just like we did for proportions. I would have to say what mu is. So mu is the true mean battery life, AAA battery life, and the units hours. All right, so that's step one. So that hasn't really changed from a one prop z test. Now we're talking about mu, not p. Now we do the conditions and name the test. So the conditions for this would be a t-test. You really wouldn't need to say means. You could t-test for mean, but people know that if you're talking about the t-test, then you're talking about means. You'd have to assume, once again, so for this problem, let's say this was in the notes, they told you that you had a sample that was an SRS. They have a sample in this problem, so the information would have to be given that they have a sample of size 15. The X bar is 33.9 hours and the standard deviation is 9.8 hours. So that 10% rule is certainly satisfied because we're going to have more than 150 batteries in the stock of the company, right? Otherwise, why go into business? The third condition, as always, is that normality or large counts. And for means, it's different, right? Proportions, we use the NP and Q. We don't have a proportion here. So we have to rely either on the central limit theorem, which we don't have here because the sample size is 15, or that the original population was normal, which forget where I took this problem. I'm not quite sure that's true, but let's just say that normality here was given as the original population was normal. If I didn't have that scenario, then I'd have to take the actual data and make a box plot, just like we did for confidence intervals, and make sure we didn't have outliers, and make sure that it wasn't grossly skewed in one direction or the other, okay? Make sure that if you did make a box plot or normal probability plot, you show that in that part. Now, for a t-test, the test statistic is going to be the t. Right? In this step on calculations, it's always nice to have a sketch. The assumption in the null is the center. And here we have an x bar that's pretty far away, but is it far enough away? So we got the mu is the center, and the statistic is where you are looking for the probability to the right, because it's a greater than test. Okay? So the test statistic here, t, is the statistic x bar minus the parameter, which is the center, mu and the null, divided by the standard deviation over the square root of n. Right, so this really hasn't changed from when we did calculations like this back in chapter 7. Now we're just doing it in the context of a hypothesis test. So you'd plug everything in, 33.9 minus 30 over 9.8 over the square root of 15. And this is where I wouldn't even do this arithmetic on my calculator. I would pick up my calculator and I would do a t-test. All right, so let's show you that. Okay, the t-test is located, if you go to stat tests, right, that's number 2. And when you pull that up, you have the option of putting it on data or statistics. If I put it on data, notice what it's doing. It's saying where's your list that you're using. So you'd have to have the actual data there inputted into L1 or L2, wherever you want to change that to. I have statistics here. Okay, so I would put in the following. I would put in mu naught, so mu in the null is 30. And then I would say the x bar they gave me is 33.9. The standard deviation was 9.8. And the sample size was 15. So when I do that, and it's a greater than test, so it's on the right one, right? I'm going to calculate that. That's giving me everything I need to finish the test. The t is that test statistic. It's not looking good because 1.54 away isn't great, right? Sorry about that. So t equals 1.54, and the p-value, which I get right from the screen, is 0.0728. Okay, so at the 0.05 level, okay, this would not be statistically significant. I would say in my conclusion, just like we wrote our conclusions for the one prop z-test, we're going to write them in the same way. We would say, since the p-value of 0.078 is greater than alpha 0.05, we failed to reject the null hypothesis. We do not have sufficient evidence to say that the true mean battery life is greater than 30. So they've got to keep working on this. They don't have the evidence. Now what I wanted to show you is that sample size really does have an effect on the p-value, okay? If we go back to the t-test one more time, and we leave the statistics in there and just change the 15 to 50, look at what happens to the p-value. That p-value now is pretty darn small, okay? So sample size, if you can afford it, what probably happened here is that in testing the battery life, you're wasting that product. So the company might not want to sacrifice as many batteries as that, but if you want to show significance, sometimes you need to do that in order to get a p-value that's low enough. Now, there is a chance that if you did have a greater sample, it would be more representative of the population, and perhaps the average, then it would be more difficult to get an average statistically significantly, greater than 30, okay? But there's a lot in this section also about paired data. I'm going to talk about that in the class sessions. This is a good test when you have match pair, a before and after measurement. You look at the change in the two numbers, and then you look just at that list of data. So please look at my notes for 9.3. Please work on 9.3 A and B and the submit. That's all due Friday this week. And please keep an eye out for my next video on 10.1 that I'm going to want you to watch and try before class next week. Okay. All right, folks, have a great day. Be safe and take care of each other.